An electric tug pulls this equipment trolley. The towbar sensor reads 500 newtons. The trolley pulls the tug backwards with the same force, yet they both accelerate forwards. Why do equal and opposite forces not cancel in this case? Start by choosing one object. A free body diagram shows only the forces acting on that object. If we choose the trolley, we include the pull from the tug, rolling resistance, its weight, and the normal contact force from the floor. A force exerted on the tug belongs on a different diagram. The resultant force is the single force that would have exactly the same effect as all of those other forces on the chosen object. Add those forces as vectors. First, let the trolley move at a constant velocity. The towbar pulls forward with 100 newtons and rolling resistance acts backwards with 100 newtons. The normal contact force and the weight also balance vertically, so the resultant is zero, although four forces are present. Newton's first law says that an object remains at rest or continues with a constant velocity unless a non-zero resultant force acts on it. Constant velocity means constant speed and constant direction. Now disconnect the tug. Rolling resistance still acts backwards, so the resultant is backwards. The trolley may still be moving forwards, but now it accelerates backwards and therefore it slows down. A moving object does not require a forward force to keep moving. This real trolley slows because a resistive force remains. Reconnect the tug and let the towbar force rise to 500 newtons. Rolling resistance is still 100 newtons. The vertical forces cancel, so take forwards as positive and add the horizontal forces. The resultant is now 500 minus 100, i.e. 400 newtons forwards. Newton's second law states that for constant mass, the resultant force on an object equals its mass multiplied by its acceleration. F subscript resultant equals ma. The trolley and case have a combined mass of 200 kilograms. Rearranging gives acceleration equals to a resultant force divided by the mass. 400 divided by 200 gives 2.0 meters per second squared in the forward direction. Acceleration points in the direction of the resultant, not necessarily the velocity. A trolley moving right with a resultant to the left accelerates left, and therefore it initially slows down. The equation also shows the role of mass. Keep the resultant at 400 newtons, but double the mass to 400 kilograms, and the acceleration halves to 1.0 meters per second squared. More mass means less acceleration for the same resultant force. We can verify the relationship experimentally. Keep the mass fixed, vary the resultant force, and measure the acceleration. A graph of resultant force against acceleration should be a straight line through the origin. Its gradient is the mass. Return to the two 500 Newton forces. The tug's force acts forwards on the trolley. The trolley's force acts backwards on the tug. They belong on different free body diagrams. Newton's third law says that if object A exerts a force on object B simultaneously exerts an equal and opposite force of the same type on object A. They are two parts of one interaction applied to different objects, so they can't cancel on either free body diagram. And this exposes a common mistake. Weight and normal contact on the trolley may be equal and opposite, but they are not a third law pair. They both act on the trolley and come from different interactions. Why does the tug accelerate? On its own diagram, the floor pushes the driven wheels forwards. This is greater than the backwards pull from the trolley and the tug's resistance, leaving a forward resultant. Now choose the tug and trolley together as one system. The towbar forces are internal and cancel each other. The external force from the floor is greater than the external resistive forces, so the complete system has a forward resultant and accelerates. The method is the same throughout. Choose the object, draw only the forces acting on it, and add them as vectors. A zero resultant leaves velocity unchanged. For a non-zero resultant, use F subscript resultant equals ma. Use the third law to connect the forces on different objects, not to cancel the forces on one diagram. Next, we're going to clear up the difference between mass and weight.